This video is going to discuss the basic concepts of designing a system in VHDL code. So let's start out with the way that I typically like to think of a system is I think of it in the top-down aspect. And that is, I'm going to look at the big picture first and then design it from the bottom up, but describe it from the top down, if that makes sense. By that I mean I'm going to look at the entire system as a whole. So let's design something that has two 4-bit inputs. So I'm going to have a input A and a 4-bit input B, and I want to select between adding or subtracting A and B. So I would either do some function that adds A plus B, or I'm going to do a function that subtracts B from A. So I'm going to have a third input that's a single bit. I'm just going to call it add sub. So I'm going to draw a entity box here. And on the output, if I add two 4-bit numbers, I could have 4 bits of a sum, and I could have a carry out. So I'm going to say sum and a single bit that is a carry out. Now this is the entity, the top level entity of my entire system. So I might have switches over here as my inputs, might have some LEDs over here as my outputs. Now let's look inside this, just one little level here. And what I want is a function inside here, some component that is an adder. And then I want a separate thing, which is a subtractor. And let's say that my inputs are directly wired to both of these objects here, both of these components. So literally what's happening is that whatever my inputs of A and B are, they are being added up here and they're being subtracted here simultaneously, because these things are working in parallel. They don't rely on one another. They're just hardware, different circuits altogether. And I only want to forward my outputs from each of these things to my LEDs based on what operation I'm doing. So what I can do is I can have a selector, and a selector in this case could be a simple mux. And for my A input, for my mux, I'm going to use lowercase a there. I'm going to take my adder and I'm going to use lowercase b to describe the output of my subtractor. And this is a little weird, but what I'm going to do is technically the adder is going to be outputting 4 bits of a sum and a carry out. The subtractor, we're going to say it's going to do the same thing. So total, there's going to be 5 bits coming out of here. I'll have 4 of them going up there and 1 of them coming down to my carry out here. The next thing that I want to do is a mux, or a multiplexer, can select between the inputs, whichever one of these I want to be forwarded to my outputs. And again, these are 5 bits apiece. So the way that it selects that is by a selector line. And this selector line, if I put a 0 here, it connects A to the output. If I put a 1 there, it's going to connect B to the output. So what I could do is have this wired over here to my add subtract button. So let's put some values on here. If I have A as 0, 0, 0, 1, and I have B as 0, 1, 0, 1. If I add these two together, I'm going to get 0, 1, 1, 0 as my sum, and then I'm going to have a 0 in my carry out. So this is the, we'll make this the color of the adder. Let's take another color here, and let's do the operation of A minus B. Well, we don't normally do subtractions here, right? So let's convert this to the 2's complement, which would be 1, 0, 1, 0 plus 1, 1, 0, 1, 1. So we rewrite this as 0, 0, 0, 1 plus 1, 0, 1, 1. And if I do the math here, I have this value, and again my carry out is a 0 in this case. So I have these 4 bits are going to be right here, as well as the carry. They're going to be coming out right here. And again, I'm going to make green be the color of the subtractor here, and yellow the color of the adder. So let's look at what happens when I have a 0 on my adder subtractor input here. Well, this 0 goes into the select line of my multiplexer, and that causes A to be wired to my output. And so my output ends up getting the value of let me undo that. So my output ends up displaying the value 6 on my LEDs. If I instead put a 1 on my adder subtractor, that goes into my multiplexer, and that selects my subtractor values to be forwarded to my output. So my LEDs are going to instead display these values. So that's the general concept of this particular top level design, right? So I said I wanted a thing that I could add or subtract 2 4-bit binary numbers. Well, that's part of the design, because I have to design these adders, these subtractors, and these multiplexers. So what we would do is we can open up what's inside my 4-bit adder. can look inside that. And inside a 4-bit adder, you have, let's see the easiest way to draw this. I have 4 1-bit adders. And I'm going to be explicit here with my naming of my inputs, because it's going to be a little easier, I think. So this is my A0 and B0. This is my A1 and B1. A2, B2, and A3, B3 inputs. And the way that works is if I have, A3, A2, A1, A0 plus B3, B2, B1, B0. These are the individual bits. And so what each one of these little blocks does is it adds these 2 bits together, and it gives me a sum and a carry out. Now, the funny thing about this is if I add 1 plus 1 here, I get a 0 right here, and then I have a carry in to the next stage, right? The next column. So that's what I have to do. So that's my carry out. It goes out here and into a pin here called the carry in. And I'm actually going to do that on all of these. I'm not going to label them all, but my carry out from one stage goes to the carry in of the next stage. And the final carry out comes out here. So I could just erase these names here. And just draw them out to the ends. So this is my sum 0, sum 1, sum 2, and sum 3. So if I go back to looking at this, that's my 4 sum bits right here. Oops. My 4 sum bits plus my carry out bit. And so if I go back here, I've got my 4 sum bits and my carry out. So looking at this, you think, oh, okay, so now I know what an adder is made of. Not quite. Each of these is another box here. So this first one here is called a half adder, and these other ones are called full adders. And we have to actually design each one of these. So in our hierarchical design here, let's look at what a half adder is. So inside of a half adder, I have an A input, because it's a single bit, and a B input. I have a sum output and a carry output. With everything that we're doing here, I'm keeping the inputs on the left and the outputs on the right. So, what is a half adder? What are the functions of a half adder? How do we design this? Well, we can just make a truth table. So A and B are my inputs. And I actually have two outputs, and I'm going to abbreviate and just put sum and carry. I'm going to just put S and C. So, no, actually I'll do that one. That's my sum, that's my carry. So let's look at what we want to happen. So if I add 0 plus 0, what should my sum be? Should be 0. And if I add 0 and 0, I shouldn't have any carry out either. Looking at the next step here, if I add 0 and 1, my sum should be a 1. My carry should be 0, because I'm not carrying anything out when I do that. If I add 1 plus 0, I get the same thing. I don't have a carry, and my sum should be a 1. And if I have a 1 plus 1, then I end up carrying 1, and my sum becomes a 0. Because 1 plus 1 is 2, which makes me have to put a 0 in my sum, and I carry out a 1 to the next column. So looking at individual outputs here and here, how can I build a circuit that does that? Well, this is a particularly simple example. If you look at this pattern here, you can recognize that that is a simple logic gate that we should be familiar with. And also, this is a logic gate we should be familiar with. So the sum is the function of an XOR gate, and the carry is the function of an AND gate. So that's what I'm going to do. I'm going to draw an XOR gate with its output to my sum. I'm going to draw an AND gate with an output to my carry. And I have my A inputs here, my B inputs here, and so now I've broken it down to logic gates. So this is my half adder. So if I'm doing this in VHDL, what I could do is I could build my half adder as an entity first. The entity has two inputs, A, B, two outputs, sum and carry out. And in my architecture, what I could say is sum gets the value of A XOR B, and carry out gets the result of the A and B operation. So this would be what lives inside the architecture of the VHDL code describing a half adder. Once I've done this, I can use that in a component here. So I would have a different VHDL file, and it would be an adder. That's what I would call it. It'd be entity adder is, I'd have these all as inputs, these all as outputs, and then I would instantiate my half adder inside of it, just like I'm using logic gates themselves. If you kind of zoom into those are really just transistors, right? Well, a half adder is really just a layout of logic gates, and so I can use this half adder inside my adder entity. The same thing as a full adder. I'm not going to go through and design all of it, but once you design these individual components, you can bring them into other entities, other architectures in here. And so you're going to do that with the adder. So you build a 4-bit adder here, and then we go up again and That's just going to be this box here. We then need to design a circuit that subtracts. So we can zoom into the subtractor, we can figure out how many components it's made of and what each of those components are, and then we can zoom into each of those components and design them. And so we have to zoom in from this top level schematic into one of the mid levels and then into the lowest level here. And then we're going to design the VHDL code for this element, use it as a component in this element, and then use this entire thing as a component in this element. And again, we do that for each one of these boxes inside here, the multiplex or whatever we might have inside this. It doesn't have to be this circuit. It could be a much bigger, more complicated thing. It could be a DSP or a processor or something like that, so it had different components but all the same kind of concept. And so that's what we're basically doing. We're building these little Lego blocks of functionality and then combining them together. And just like with Lego blocks, you can build a house and then you don't refer to that then as 47 2x2 Lego blocks and whatnot. You refer to it as a house at that point. So we're doing the exact same thing. We're going to build stuff out of logic gates, put a box around it, and call it whatever that object is, like a multiplexer, for instance. And then we're going to use that as a functional block. We know how it works, the inputs and outputs relationships, and we can use that to build more complicated, larger circuits. There's a software that we can easily do this in. The software is called Multisim. There's a really cheap student version, but it should be free on our computers in the labs. If you go to File, New, and select PLD Design, a PLD is kind of like, you can imagine it almost as a precursor to the FPGAs we're going to be using in class. We're going to create an empty PLD because we're just going to mess around with the concept here. We can name it whatever at the moment, but this would be, maybe we would say like half adder, for instance. And we're not actually going to implement this on hardware, we're just testing right now, so I don't really care what these are. Just click finish. And so we're going to say, okay, here's a half adder. I'm going to use these little areas here to put inputs and outputs on this thing. So this is an input connector. I'm going to name that A. I'm going to copy and paste that here, make that my B, and I'm going to put an output over here for my sum, and I'm going to copy that, paste it, and that's my carry out. And so now I have inputs and outputs, just like I have in my entity of my VHDL code, right? Now I'm going to place a logic gate here. I'm going to use a 2 input AND gate for my carry out, and I'm going to use a 2 input XOR gate for my sum. Now again, that is when I design that's what the half adder does, right? So, and I just realized I may be a little out of my viewing range here. Okay, so I got the input tab. This thing right here comes from this button. I've got the output tab from this button. And I opened a PLD design from going to File, New, and clicked on PLD Design. So once I have these gates here, what I'm going to do is wire them. So if you look at our design, we have A and B are the inputs to the XOR gate, and then A and B are also the inputs to the the AND gate here. So let's just wire that. The way you wire in Multisim is you just put your mouse over the endpoint of something, or you could say place wire and wire it to where you want it to go. So I want that to be A and B. I want this to also be A and B. And you'll notice there's a little tiny dot here, and that dot is called a junction. Whenever that dot is there, that means that this wire, this horizontal one, and this vertical one are connected. If you notice just under that, there is no dot. So that means that this wire and this one are not connected. So only A is connected to the top inputs of both of these. We're going to connect our outputs here, and we're going to save this PLD design. So I'm going to say it's a half adder. And now I can go to my design toolbox and say I want a new PLD design. And I'm just going to click whatever for that. And if I want to use the half adder, what I can do is I can actually place where there we go, hierarchical block from file. So I'm going to basically right now this would be this new level here. If I save this or rename this, this one would be the adder from our example here. So this is our half adder, and I would use that as a block inside the next level of the adder. So that's what I have here is my adder, and I'm going to import from the hierarchical block. That just basically means I'm going to take my half adder and drop it in here. Now if you notice, the half adder looks really similar to the half adder we have in here. If I just look at this, I have an A input, a B input, a sum output, and a carry output. And that's exactly what I have here. So now let's actually put some interesting things on here and test it out. That's the beauty of Multisim, is you can actually simulate. So I'm going to place probes on the output. I like the blue probes. So there's my sum probe, and I'm going to put my carry probe, and I'm going to do an interactive digital constant for my source of each of these. And I'm going to kind of clean this up a bit. For both of these, I'm just getting rid of all the excess text here. And so this is going to be my A input. So I wire that there. This will be my B input. This thing is my sum. And this thing is my carry out. And so my sum and my carry out are going to act as my LEDs. So I am going to click my run button, which will run the simulation. If you remember what our truth table was, we have, I'm doing screencast, I have 1,000 tabs open, so it's just taking it a minute. If you remember our truth table for the half adder, let's try to zoom that just exactly where it needs to be. And then here, there we go. So, if you remember our truth table, when A is 0 and B is 0, our sum is 0, our carry out is 0. Let me swap these so that they will match our truth table outline here. Okay, again, there's no junction there. That is not connected. So it's just sum, just wires out to here. So as I run my simulation, I can compare my inputs here to my outputs. So 0, 0 for my A and B gives me 0, 0 on my outputs. If B becomes a 1, then I should expect my sum to be a 1. So that lit up the LED. Alternatively, if A is a 1 and 0 is a B, then I also get a 1 on my sum and a 0 on my carry. But if 1 and 1 are my inputs for A and B, then my sum itself is a 0 and my carry out is a 1. And so this does the function of adding two individual bits. And so if I wanted to build our overall design here that we discussed in the beginning, I could do that within Multisim and do it as schematics, because I can go all the way down to the lowest level. Or I could code those things in VHDL and Vivado, which is the tool that we're using in class. Multisim makes it visual and you can see what's happening easier. And sometimes I don't usually use Multisim, but I like to sketch out my the general layout of my designs. So I have my top level schematic of the entire system, and then I draw the components that are living within that top level, and then depending on how complicated each of those components are, I'll break those into smaller and smaller components until I get to the lowest level I can implement in VHDL, and then I build up the total system from there. So that's a long basic introduction to designing systems in a hierarchical system using VHDL or schematic entry or whatever you would like to use. And an introduction, I guess, to Multisim for those of you who've never seen it. So, and yeah, we can continue doing this, going from the adder, the half adder to the adder to the top level schematic if we'd like, and continue building inputs and outputs on these things until we build our full system. But that's it.